What is the specific problem that the proposed method aims to solve in the field of digital hardware design?
The specific problem that the proposed method aims to solve in the field of digital hardware design is the automated placement of components, particularly macros, on a two-dimensional physical chip based on a connectivity graph netlist of the components. The traditional macro placement process is time-consuming, expensive, and relies heavily on heuristics from commercial tools. The proposed method utilizes diffusion models to generate near-optimal chip placements for given netlists, addressing the limitations of existing reinforcement learning approaches. By leveraging generative models, the method can be trained offline at scale and used zero-shot on new netlists, producing placements that consider the impact on key metrics such as power, area, and performance of the chip. The goal is to automate and optimize the placement process, especially for macros with high connectivity, to improve chip performance and efficiency.
How does the proposed method work, and can you illustrate it step by step?
The proposed method leverages diffusion models to generate near-optimal chip placements for a given netlist. The process involves training a denoising diffusion probabilistic model, DDPM, to iteratively denoise samples using Langevin dynamics, resulting in a fully denoised output as the generated sample. The model architecture includes interleaved graph convolutional layers and multi-headed attention layers for computational efficiency and expressiveness. The model receives 2D sinusoidal position encodings, in addition to original coordinates for improved precision in placing small objects. The training process involves pre-training on synthetic data, followed by fine-tuning on a smaller set of large circuit examples. The model performance is evaluated based on legality and half-perimeter wire length (HPWL) metrics. Guided sampling is utilized to optimize for downstream objectives without additional training, using a weighted sum of potentials for legality and HPWL. The model is then applied to real-world circuits by clustering standard cells and using the diffusion model to generate placements for macros and clusters. The final mix-sized placement result is obtained through a two-stage workflow involving the diffusion model and DreamPlace for global placement. Ablations over model elements demonstrate the importance of components like sinusoidal encodings and attention layers for performance. The method addresses limitations such as the transferability of models to out-of-distribution circuits and the reliance on guidance for sample optimization.
What are the theoretical or practical benefits of using diffusion models in chip placement compared to traditional reinforcement learning approaches?
The theoretical and practical benefits of using diffusion models in chip placement compared to traditional reinforcement learning approaches lie in their ability to address key limitations of RL methods. Diffusion models can be trained offline at scale, allowing for zero-shot application to new netlists without the need for extensive additional training. This contrasts with RL, which is sample inefficient and requires significant training for each new netlist. Additionally, diffusion models can simultaneously place all objects in a chip layout, avoiding the sequential placement challenges faced by RL-based methods where suboptimal choices early in the process cannot be easily reversed. Furthermore, diffusion models leverage powerful generative models to produce near-optimal chip placements, offering better optimization results compared to RL approaches that heavily rely on heuristics. The use of diffusion models, as described in the paper, allows for efficient and scalable placement of macros on a chip, leading to improved metrics such as power, area, and performance without the need for extensive human input or costly commercial tools.
How is the performance of the proposed method evaluated and tested in the paper?
The performance of the proposed method is evaluated and tested in the paper through various means. Firstly, the paper uses evaluation metrics such as legality and half-perimeter wire length (HPWL) to assess the quality of the generated placements. Legality measures how easily the placement can be used for downstream tasks, while HPWL serves as a proxy for chip performance. The paper focuses on ensuring legality, by avoiding object overlaps and keeping objects within the bounds of the canvas. HPWL is used to evaluate placements before routing, with the goal of generating legal placements with minimal HPWL. Additionally, the paper conducts experiments on synthetic datasets, Synth-M and Synth-L, and real-world circuits from public benchmarks, ISPD 2005 and ICCAD 04, to test the model's performance. The experiments show that the model achieves legality better than 0.9 and HPWL ratios close to 1, indicating that the model can learn near-optimal placements in both realistic and synthetic circuits. Furthermore, the paper explores the impact of pre-training datasets, ablations of model components, and the use of guidance to optimize generated samples. The results demonstrate the effectiveness of the proposed method in generating high-quality placements for mixed-size circuits, showcasing reasonable zero-shot transfer to real-world circuits and improvements in placement quality compared to existing optimizers like DreamPlace.
What results were achieved by the proposed method on synthetic and real-world circuits, according to the paper?
The proposed method achieved legality better than 0.9 and HPWL ratio very close to 1 on synthetic circuits, validating the model design's capability to learn near-optimal placements. The experiments with different model sizes on synthetic circuits showed significant performance improvements as the model size increased, with legality increasing and HPWL ratio decreasing with bigger models. Additionally, the model showed reasonable zero-shot transfer to real-world circuits, placing densely connected standard cell clusters and macros together in a mixed-sized placement problem. The model was able to generate near-optimal placements for macros and clusters, improving the placement quality of DreamPlace while saving runtime. The method demonstrated the efficacy of the initialization in impacting the final placement quality and stabilizing the runtime, showing promising results for tackling the placement problem in both synthetic and real-world circuits.
What are the limitations of the proposed method mentioned in the paper?
The limitations of the proposed method mentioned in the paper include the potential challenges associated with synthetic datasets with shorter wire lengths, which may lead to poorer transferability to out-of-distribution circuits. Another limitation is the reliance on guidance to optimize generated samples, which can restrict the achievable HPWL, since it biases the model towards a subset of the training distribution. Additionally, the method requires a final optimizer to complete mixed-sized placements of millions of cells, and the quality of this optimizer can impact the final placement quality. Further exploration of optimization methods that involve fine-tuning the model, such as reward-weighted regression or DDPO, is suggested as a promising area for future work to address these limitations and enhance the performance of the proposed method.